In the third quarter of 2025, the world witnessed a technological catastrophe that would redefine the relationship between physics, engineering, and digital civilization. The great internet outages of 2025 were not merely a failure of infrastructure, they were a convergence of cosmic physics, electromagnetic chaos, and human vulnerability. As a physicist observing the event unfold, it became clear that this was not just a technological failure, but a profound lesson in the fragility of the systems that bind modern society together. Prelude to the collapse. The first anomalies appeared in early July 2025. Network latency spikes were detected across the Pacific undersea cables connecting Asia and North America. These cables, stretching thousands of kilometers across the ocean floor, rely on optical amplifiers powered by precise electrical systems. When those systems began to fluctuate, engineers suspected routine faults. But the pattern was global. Within 48 hours, similar disruptions appeared in Europe, Africa, and South America. Internet exchange points, the digital crossroads of global communication, showed erratic routing behavior. By mid-July, the world's digital nervous system was faltering. From a physicist's perspective, the timing was ominous. Solar observatories had just recorded one of the most powerful coronal mass ejections, CMES, in decades. The Sun, in its 11-year magnetic cycle, had entered a phase of heightened activity. The CME that erupted on July 9, 2025, was a monster. Billions of tons of charged plasma hurled into space at over 2,000 kilometers per second. 2. The solar storm and the physics of disruption. When a CME collides with Earth's magnetosphere, it compresses the planet's magnetic field and induces geomagnetic currents in conductive materials. These currents can overload power grids, disrupt satellites, and interfere with radio communications. In 2025, the CME's impact was amplified by a rare alignment of Earth's magnetic poles and the solar wind's orientation. The interplanetary magnetic field IMF was southward, allowing maximum coupling with Earth's northward field. The result was a geomagnetic storm of unprecedented intensity, comparable to the Carrington event of 1859, but in a world utterly dependent on digital infrastructure. Satellites in geostationary orbit experienced induced currents that scrambled their onboard electronics. Some lost orientation, others entered safe mode. The ionosphere, a layer of charged particles critical for radio wave propagation, became turbulent. GPS signals degraded. High-frequency communications failed. On the ground, long-distance fiber optic cables, though immune to electromagnetic interference in their glass cores, relied on metallic repeaters and power lines that were not. The induced currents caused voltage surges, damaging amplifiers and routers. The global internet backbone began to fracture. Third, the domino effect. The internet is a complex adaptive system, a network of networks. It is designed to reroute data when one path fails. But in Q3 2025, the scale of the disruption overwhelmed these redundancies. Major cloud providers, Amazon Web Services, Google Cloud, Microsoft Azure, reported simultaneous slowdowns. Content delivery networks, CDNs, that cache data near users began to fail. Data centers overloaded as they attempted to reroute traffic through unaffected regions. The failure cascaded, banking systems froze. Air traffic control networks reverted to manual coordination. Smart grids lost synchronization. Hospitals struggled to access cloud-based patient records. The physics of the failure was clear. The electromagnetic storm had triggered a non-linear cascade. In complex systems theory, this is known as a critical transition, a point where small perturbations cause massive systemic shifts. The internet had reached its tipping point. 4. The cybernetic exploitation. While engineers battled the physical consequences of the solar storm, another threat emerged: human exploitation of chaos. Cybersecurity experts discovered that multiple state-sponsored hacker groups had launched coordinated attacks during the outages. They targeted the Border Gateway Protocol, BGP, the system that determines how data travels across the internet. By injecting false routing information, they caused data to be misdirected or dropped entirely. Some regions became isolated digital islands, unable to communicate with the rest of the world. From a physicist's standpoint, this was a form of information entropy, a deliberate increase in disorder within the system. The attackers exploited the weakened state of the network to amplify chaos. V. The human dimension. The outages revealed the extent of humanity's dependence on invisible systems. In the United States, stock markets halted trading. In Europe, air traffic controllers coordinated flights using radio and paper charts. In Africa and South America, mobile banking networks collapsed, leaving millions without access to funds. Social media platforms went dark, cutting off billions from their primary source of news and communication. Misinformation spread through offline channels, fueling panic. Hospitals reverted to paper records. Logistics companies lost track of shipments. Even weather forecasting systems were disrupted as satellite data streams went offline. The digital blackout had become a humanitarian crisis. 6. The physics of recovery. By late August 2025, the world began to recover. Engineers, physicists, and data scientists collaborated to stabilize the network. The first step was to restore satellite orientation. Using ground-based laser communication systems, operators re-established contact with affected satellites. Power grids were recalibrated to handle geomagnetically induced currents. Artificial intelligence played a crucial role. Machine learning algorithms analyzed trillions of data points to identify weak links in the network and predict where failures might occur next. These AI systems acted as digital immune responses, isolating damaged nodes and rerouting traffic dynamically. From a physics perspective, the recovery process resembled self-organized criticality, a system naturally evolving toward stability after a period of chaos. 7. Lessons in electromagnetic vulnerability. The Q3 2025 internet outages forced scientists and policymakers to confront a fundamental truth. The digital world is built on physical foundations that are vulnerable to cosmic forces. The event reignited interest in space weather physics, the study of how solar activity affects Earth's magnetosphere and technological systems. Governments began investing in early warning satellites capable of detecting CMES hours before impact. Physicists proposed new shielding technologies for undersea cables and satellites, including superconducting materials that could dissipate induced currents. Quantum communication networks, immune to electromagnetic interference, gained renewed attention as a potential backbone for future internet infrastructure. 8. The cyber-physical frontier. The 2025 crisis also blurred the line between physical and digital threats. The combination of a natural cosmic event and human cyber attacks demonstrated that the next great conflicts may occur in the cyber-physical domain, where physics and information warfare intersect. Physicists began collaborating with cybersecurity experts to model the internet as a complex thermodynamic system where energy, information, and entropy interact. This interdisciplinary approach aims to predict how digital networks respond to external shocks, much like how physicists model earthquakes or plasma instabilities. 9. The socio-technical reckoning. Beyond the science, the outages sparked a philosophical reckoning. Humanity had built a civilization dependent on an invisible lattice of photons and electrons, a system so vast and intricate that no single entity fully understood it. The blackout revealed that resilience, not speed, must be the new priority. Decentralized networks, local data storage, and analog backups became essential components of national security. The event also reshaped public perception of science. For the first time, the physics of the sun, the magnetosphere, and electromagnetic induction became topics of global conversation. The cosmos had reminded humanity of its power. X. The legacy of 2025. By the end of 2025, the internet was largely restored, but the scars remained. The great internet outages became a case study in complexity, resilience, and the limits of human control. For physicists, it was a moment of clarity, a demonstration that the laws of nature still govern even the most advanced technologies. The same electromagnetic forces that power the auroras can also cripple satellites. The same plasma physics that drives solar flares can disrupt global communication. The event inspired a new generation of research into magnetohydrodynamics, quantum communication, and resilient network design. It also led to the creation of the Global Space Weather Defense Initiative, a coalition of scientists and engineers dedicated to protecting Earth's technological infrastructure from cosmic threats. 11. Reflections from a physicist. The Q3 2025 Internet outages were not just a technological failure, they were a reminder of humanity's place in the universe. The sun, indifferent and ancient, reminded us that our digital world is still bound by the laws of physics. In the end, the crisis taught a profound lesson. Progress without understanding is vulnerability. The internet, like any physical system, must obey the principles of energy, entropy, and equilibrium. The blackout of 2025 was a warning, but also an awakening. It showed that the path forward lies not in conquering nature, but in harmonizing with it. The next era of technology will not be defined by faster speeds or larger networks, but by resilience, by the ability to withstand the unpredictable rhythms of the cosmos. And as the auroras of 2025 faded from the sky, humanity began to build again, this time with the wisdom of physics guiding the light of the digital age.